To analyze the joint here, first consider we have a weld. We have two plates here, plate 1 and the plate 2. And this one is exactly the triangular shape which is representing the fillet weld. But in fact here when we are doing the welding, so you will find here the shape of the weld is something like this. This one is representing the mixture of the parent material 1, 2 and the filler material. And here we have a fillet joint. So this one is fillet joint. So this one is representing the mixture of two metals and the filler material. And there is a little bit of extrusion from this edge. So this here is called as reinforcement. And near the plate here we get a fusion area. So this one is representing the fusion area, which one is the parent metal and the filler material. So this one is also representing the fusion area, which one is parent material and the filler material. The fusion area is formed near the parent metal and the filler, and the parent metal and the filler. Fusion area and the reinforcement are the two different things in the fillet weld. So this height here is called as the leg height equal to h, as well as this base is also equal to leg height equal to h. So this figure is enlarged here. We have a leg height is equal to h as well as the leg height equal to h. So this one is an isosceles triangle. They are perpendicular to each other, and therefore this angle will be 90 divided by 2, that equal to 45 and 45. This corner here is called as root, and if we draw here any line on the face from the root angle equal to theta, then it will be called as throat. So throat has a length equal to t. In that case we can define two area. One is based on the fusion area and one is based on the throat area. Here L represents the length of the weld, and we have a throat area. In that case will be T multiplied by the length of weld equal to L. And we have fusion area, which one has the leg size equal to H multiplied by the length of weld equal to L. Actually we are interested in the throat area, and we are interested in the minimum throat area where the sharing will occur. We are not interested in the fusion area. It is very clear here, the fusion area is greater than the throat area. So we want to develop the relation between the throat angle theta and the leg size equal to h. So we'll consider a one triangle ABC. AB represent here the throat dimension, AC represent here the edge dimension. This angle is same as equal to theta. If this angle is theta, this angle is equal to 45, then we can calculate this angle. We have this angle is same as equal to 180 minus 45 minus theta, which is same as equal to 135 minus theta. Now we know the angle opposite to leg size, that equal to 135 minus theta, and we know the angle opposite to T, that equal to 45. To develop the relation between T and H, we can apply the law of sine. According to the law of sine, the side is proportional to the sine of the angle opposite to it. So we have T divided by sine of 45. So we have T, opposite angle is 45, and you have to take the sine of it, that is sine of 45 is equal to H, which one is leg size, divided by the sine of the angle opposite to it, that is sine of 135 minus theta. So we have T is equal to H multiplied by sine 45 divided by sine of 135, sine of 135 minus theta. So we'll expand the sine here and we'll develop the relation for T. So we have T is equal to H into sine of 45 divided by sine of 135 into cos of theta minus of sine of theta into cos of 135. Now since we are familiar with the sine of 45, sine of 45 is same as 1 by root 2, that is 0.707. Sine of 135 is also equal to 0.707, and we have cos of 135 is negative value is 0.707. So we'll do this substitution here and we'll solve for T. So we have T is equal to H into 0.707 divided by sine of 135 is also 0.707 into cos of theta minus 135 cos minus minus become plus is 0.707 into sine of theta. So 0.707, 0.707 and 0.707 will cancel out. So let's cancel 0.707, 0.707 and 0.707. So throat thickness we can very well calculate using the leg size, and we have throat thickness T is same as equal to the leg size equal to H divided by cos theta. So we have cos of theta plus sine theta. Now this one is a very useful relation. I will require this relation to find the value of shear stress in the fillet weld. In fillet weld we'll consider two cases. In the first case we have the direction of force F and the axis of the weld, they are parallel to each other. So when the axis and the applied force are parallel to each other, that is called as the parallel loading. Now because of a parallel loading here, the bottom area and this force will be parallel to each other. So on bottom area we have the force is acting equal to F, as well as on the side area force is acting in this direction. When the force and area is parallel to each other, then the shear will be developed. So in case of parallel loading, both the plate exert a shear load on the weld. When the axis of the plane is perpendicular to the direction of force, so this one is representing axis, which one is perpendicular to the direction of force, it will be called as transverse loading. Now if you observe carefully about the bottom plane, on the bottom plane we have the area will be this area and force is applied in the same direction on the bottom plane. Since the bottom plane and the force F, they are parallel to each other, so shear is developed by the bottom plane on the weld. But if we observe this force F, which is acting on the top side, so top side area is this area and the force is acting perpendicular to it. This time the force F is perpendicular to area and hence we have tensile, or depends, the direction is reverse, then the compressive stress is produced. So in this case we'll say the normal stress is produced, and if the force is parallel to A, then the shear is produced. So bottom plane exert a shear load, while depending upon the direction of force F, we have a tensile or the compressive stress is produced. So this one is important in the case of parallel loading. Both the bottom plate and the top plate will exert a shear load on the weld, whereas in the case of transverse loading, which one is more complicated, as one plane will exert a shear load, that is the bottom plane will exert a shear load because the force F is parallel to the area and hence we have shear load. On the top plate we have force and the area, they are perpendicular to each other and therefore we have normal stress, maybe tensile or compressive. So this situation is more complicated as compared to the parallel loading. So for analysis purpose, we'll consider here a transverse loading in which the direction of force is perpendicular to the axis of the weld. So we'll calculate here both value, that is the shear stress and the value of the normal stress, and we'll compare here which one is the higher value and which one is lower value. So we'll consider here we have a 3 plate, plate 1, 2, 3, and we have a fillet weld. Let the force applied is equal to F on the top plate. Same force is applied on the bottom plate equal to F, and on the middle plate by equilibrium this force is same as equal to 2F. Here we have a fillet weld as well as here we have a fillet weld. We know that fusion area is very large area as compared to the throat area. Let us assume here we have a length of the weld is equal to L and H is a leg size. This size also equal to H, as well as bottom size we have leg size equal to H. At any angle theta we can define the throat thickness. So let's consider one plane X at an angle equal to theta with the vertical. We already know this angle is 45 and this dimension will be same as equal to T and the leg dimension equal to H. For analysis purpose, we'll cut here at the section X. We'll develop the FBD for the top portion. So only the top portion is considered for analysis. This force is same as equal to F. The angle between the vertical and this plane will be equal to theta. So let's represent here theta. Here this dimension is same as this dimension that equal to T. That is the throat thickness. And this one is our leg size equal to H. H represent here the leg size H. So this force is exerted on the other side also, and we can resolve that force along the angle theta. One force will act parallel to the throat. So the component of this force will act parallel to the plane having the throat equal to T, length equal to L. So this one is called as the shear force Fs because it is parallel. So Fs represent here the shear force, and perpendicular to this area which will develop the tensile stress will be labeled as Fn. Here Fn is called as the normal force. So we want to show here how the value of Fs and Fn are related with respect to F and the value of theta. So this one is the same force acting on the other side will be equal to F. This angle will be same as equal to angle made with the vertical with the throat equal to theta. And this dotted line and the force are perpendicular to each other. So this angle is same as 90 minus theta. These two dotted lines are perpendicular to each other and therefore this angle will be same as theta. So this component will be cos and the other component will be sine. So as per our resolution, this force is same as equal to F. It makes an angle of theta with horizontal. Then this component will be same as our normal component Fn, which one is same as equal to F cos theta. And this one is our shear component, which is Fs is opposite. So value of Fs will be same as equal to F into sine theta. I hope this idea is clear how we resolve the force F and we get a contribution of Fs and Fn. So Fn force, which is acting perpendicular to the throat, will develop the normal stress, and Fs, which is acting parallel to the throat, will develop the shear stress. So using the value of Fs and Fm, we can calculate the stress at an angle of theta in the weldment. One value will be the shear stress, that is represented by tau. So we have shear stress is represented by tau is same as equal to Fs area A. Since we are interested in the throat area is T into L. So A stand here for throat area. Fs value we can replace as F into sine theta. So we have shear stress equal to F into sine theta divided by the area A, which is equal to throat area is T multiplied by L. Secondly, we can also show the normal stress, which will represent as sigma, is given as the normal component of force is Fn divided by again the throat area. We have a same throat area that equal to T into L, but we have normal force is given as F into cos theta divided by the throat area T into L. So we know the tau, we know the value of normal stress, and we have already shown that if we have a equal leg size, then the throat thickness at any angle theta can be given as T is equal to H divided by cos theta plus sine theta. So we'll replace the value of T in the last equation using the throat thickness. So we have shear stress tau is given as Fs divided by area, that is the throat area is T into L. Here T we can replace as H divided by cos theta plus sine theta. So cos theta plus sine theta will go in numerator and H will come in denominator. So by substitution you will get F multiplied by sine theta multiplied by cos theta plus sine theta divided by H into L. So this one is the shear stress in the form of angle theta. Naturally the shear stress is the function of theta, as well as normal stress, which is given as Fn by A. Fn we have is equal to F cos theta divided by T. T we can again replace. So cos theta plus sin theta will come in numerator. So we have normal stress is equal to F multiplied by cos theta plus sin theta divided by H into L. So we have shear stress tau is a function of theta, as well as normal stress is also a function of theta. So in this case we have tau is a function, let's say F1, and sigma is also a function of theta, let's say F2 theta. So we have a small element here. On this small element the stress will act. Let's say this axis is X and this axis is Y axis. So we'll change the orientation in this figure and we'll slightly enlarge it. We have X axis, this one is Y axis. We have a normal stress equal to sigma, and we have shear stress, which one is equal to tau. So this one is same as tau xy. We have tau xy is same as equal to tau. Now since here the tau and sigma both are the function of theta, as the theta will change, the value of tau and sigma will also change. At one particular value of theta, we have maximum value of shear stress and the maximum value of normal stress. If we use the distortion energy theory, then we can calculate the von Mises stress at an angle equal to theta, that will represent as sigma prime, which is given as under root of sigma square plus 3 times of tau square. This value of sigma is also a function of theta. So the normal stress is also function, shear stress is also function, and the von Mises stress is also function. The largest von Mises stress will occur at a particular value of theta. The largest von Mises stress occurs at theta is equal to 62.5, and corresponding maximum value of von Mises stress sigma max is equal to 2.16 times F divided by HL. Similarly, the maximum value of the shear stress is obtained by differentiating tau with respect to theta, because tau is a function of theta. So in that case we have to differentiate tau with respect to theta and we have to equate to 0 and solve for theta. So let's differentiate tau with respect to theta. So we'll differentiate this equation with respect to theta equal to 0. So I am giving you direct solution. The theta value will come out to be 67.5. Now at this value of theta is equal to 67.5, you will get the maximum value of the shear stress. So you have to substitute the value of theta equal to 67.5 in the equation of shear stress and solve for tau. In that case, we have tau max will be equal to 1.207 times F divided by H into L. So equation number 2 gives you the maximum value of the shear stress at theta equal to 67.5. Equation number gives you the maximum value of the von Mises stress at theta equal to 62.5 degree. So this one is a mathematical model in which we have taken the value of Fs and Fn at throat, which is inclined at an angle of theta. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.